Okay, so now we talked a little bit about the matched filter, and let's put the matched filter to use in our receiver. So we have, I claim the following, that this block diagram is a minimum distance receiver for PAM, and this is what we would like to do. And this is what you would like to do in your project also. So we have pulse amplitude modulation, we have some noise, we have a receiver filter, and we see here that the receiver filter is matched to h of t, which is the transmit pulse. Okay. We see that because here we have h of t, and here we have h conjugate, and then time reversed. So this is a match filter. We have the output y, and then we sample that, and we sample that once every t seconds, and t seconds is how often we transmit the pulses. Then we get y of k, and this thing here is just a fancy way of saying that we multiply y with the inverse of the energy of h. That's simply we take y and we divide by the energy of h, and then we get some a number z of k, and that we go through this slicer, which I will explain a little bit later what that is, and out we get a guess. So this is our guess or decision on AK. So this is the output, and ideally we would like to make A hat K equal AK. Then things will be good. Right? So that's the objective. And the thing which would destroy this is the noise. So let's analyze this a little bit and see what's actually going on. And let's just concentrate on the first pulse. Okay, so we take, we look at when A0 goes through this, what's going to happen? What is the output then? If we take, so let us consider the transmission of A0, i.e. AK when K is equal to 0. Okay. And we can do that, we can analyze the system looking at only this symbol if if we don't have any intersymbol interference. So let's assume that H of t is a Nyquist pulse. Actually a root Nyquist pulse. Which implies that there will be no intersymbol interference. Let's make an example of the mapper, which is not shown on this. But suppose we have two bits, B0 and B1, which are mapped, which is, they could be 0, 0, 0, 1, 1, 1, 1, 0, and 1, 1. These are the possible input bits. And then these should be translated into symbols. But we do that first by introducing this variable m, which is an enumeration of this. So this is 1, 2, 3, and 4. So that's just an enumeration of these bit patterns. And we map them then to the corresponding symbol A0. And if the input is 0, 0, which is signal index 1, then the amplitude A0 is equal to A1. Okay. If it's 0, 1, the index is 2, and we get A2, capital A2, and then A3 and A4. Okay. So this is a description of the mapper from bits via this index M to a corresponding amplitude capital A1 through capital A4. So these numbers we have chosen. Okay, and what is then the corresponding transmitted signal? Well, it's the amplitude multiplied with the transmit pulse. And since we're looking at the first pulse which is transmitted, the pulse is not delayed by anything. It's just the pulse itself. Okay. So I just complete the table here. Okay, so this is what's going on. And just want to introduce the signal alternatives here also. So S1 through S4. Okay, so a certain bit pattern is mapped to a certain index, which is mapped to an amplitude, and then the transmitted signal is that amplitude multiplied with the pulse. So this is what's going on. Right? Any questions on this? No. Okay, so then let's see now. If the noise is equal to 0, then it better be like Z of k is equal to A of k. Okay. Otherwise, we would be having a bad design. Okay. So let's see if that is the case. Let's start by, first of all, calculate the sample y0. Okay? And the y0 we get by sampling the output at time 0, and then we know that the output is then the inner product of the input with the pulse h of t. So y of 0, we know that since last hour, that this is the inner product of r and h. This is always true. So this is the integral from minus infinity to infinity of r h conjugate of t dt, like this. Okay. If the noise is equal to 0, then R, the received signal, is just a transmitted signal. We see that. If we put the noise to 0, then R is equal to S. So this integral is, just replace R with S. So it's S of t, H conjugate of t, dt. And what is S? Well, S could be one of these things. Okay. In general, S of t is equal to the transmitted symbol, which is A0. So A0 takes on one of these values. We don't know which one, but it takes on something. And then multiply that with the transmitted pulse H of t. Okay. So this is S of t. And then we should multiply with H conjugate of t and integrate for all times. So just replaced S with the corresponding symbol A0 times the pulse H of t. Okay. We can take out A0, and then we have the integral from minus infinity to infinity, H of t, H conjugate of t, dt. So this integral, what is that equal to? that has a certain name.
Energy.
Exactly. It's the energy of H. So E subscript H, so the energy of H. So this is A0 EH. Okay, now we're almost done. So Z0, okay, so now we know what Y0 is, and then we divide by EH to get Z0, okay. So Z0 is Y0 divided by EH, okay, which is then A0 EH divided by EH, which is equal to A0. Okay. Which is exactly what we wanted. Okay. So clearly, this works when there is no noise. So it's not completely stupid. That's what we can conclude now. And this thing is needed in order to scale everything correctly, so that zk is equal to ak when there is no noise. That scaling factor in itself is not super important, but it's just convenient to do this. Okay. Now, in general, we have noise, but then we can write Z0 as A0. It will always be A0. Since everything is linear in the receiver, A0 will be here, but there will also be a contribution from the noise, and let's call that N0. So if we look at the path here through the diagram, the symbol that we care about goes through this, and it ends up here. Okay, so zk is equal to ak for sure. Then the noise, the noise goes in here, goes through this filter, gets sampled. We get a noise sample here. We divide by the energy, and then we get some noise sample here. So we can always write zk as the symbol that we care about plus a noise sample. And this we can do because everything is linear here. So we can follow the signal paths independent of each other and then just use a superposition principle to add everything up together at the end. Okay. So any questions on this? Okay. Now, so we now know that this is not a completely stupid thing, but is it also the minimum distance receiver? So then what we want to do is to make sure that the output here is the output that we would get if we had a minimum distance receiver. So let's go through that derivation to see that this is indeed the case. So let us compute the distance squared, so dl squared. So what is dl squared? Well, it's the distance between the receipt signal and the LF signal alternative squared, which is equal then to the integral from minus infinity to infinity, the absolute value of r minus SL of t. Magnitude squared. Okay. So before we continue, let's state the very convenient identity for complex numbers. So if x and y are complex numbers, and we take the magnitude of that squared, because that's essentially what we have here, a complex number here, or actually complex signals. Okay, we can write this as x minus y times x minus y conjugate, like this. So a magnitude squared of a complex number is the complex number multiplied with its complex conjugate. And then we can develop this product into x times x conjugate minus x times y conjugate minus y x conjugate plus y conjugate, like this. I just multiply these two parentheses together. Okay. So what is x times x conjugate? It's the magnitude squared of x. So here we have the magnitude squared of x. What is y times y conjugate multiplied with y conjugate? What is the magnitude squared of y? And then we have something like this. So just replace the first term with x magnitude squared, kept the second term here, x y conjugate, and then minus, and instead of y times x conjugate, I conjugated the, oops, sorry, my bad. It should be here, y conjugate x conjugate, like this. The conjugate of the product is the product of the, if I conjugate the product, I simply conjugate the factors. Right? So y times x conjugate is y conjugate x conjugate, like this. Okay, so here we have a complex number. Okay, so let's write it. Okay, so let's write it like this. Minus x y conjugate plus x y conjugate conjugate. Okay, so hopefully this was not mysterious. It's just algebra. Okay, so if we have a complex number plus and add to it its complex conjugate, what do you get then? What's the real part of this? Well, it's the real part of this plus the real part of this. What's the imaginary part? Well, it's the imaginary part of this minus the imaginary part of itself. So this is 2 times the real part of the product, like this. You see that? A complex number plus its complex conjugate, the imaginary parts cancels and we get twice the real parts. Okay, good. So then, armed with this insight, we just expand this according to this equation, and we get here the integral from minus infinity to infinity of the real r magnitude squared dt minus 2 times the real part of the integral from minus infinity to infinity of r of t SL conjugate of t dt plus the integral from minus infinity to infinity of SLT magnitude squared dt. Okay. The first part here is just the energy of the received signal. The second part is the inner product of R with SL conjugate. And SL conjugate is our amplitude that we were transmitting. Okay, so it should be the LF amplitude and the pulse HOT, like this. And the last part here is just the magnitude, it's the energy of the LF signal alternative, so which is then AL squared, let's do magnitude squared times the energy of the pulse, like this. Okay, and we continue here a little bit and write this as ER minus 2 times the real part of R of t, H of t, and then we break out AL from this, and like this. So when AL is in the second thing here, we know that by definition it's the integral of R multiplied with the complex conjugate of this. So when you break out a constant factor here, we need to conjugate that into this. So this is found just from the definition of the inner product. And then we have here plus AL magnitude squared EH, like this. And what we recognize here is that this inner product is something that we've seen before. So this is simply the output of, it's the sample here, the noise-free sample. Sorry, it's the inner product of R with the impulse response H of t. So this is equal to Y0. So we have here ER minus 2 times the real part of AL conjugate times Y0 plus the magnitude of AL squared EH. I'll let you work a little bit on this. Okay. For reasons which are not super obvious right now, but will be convenient, I will break out the factor EH from this. And the first term will be ER divided by EH, then minus 2, the real part of AL conjugate Y0 divided by EH plus AL magnitude squared, like this. All right. Now we take another expression and look at that. So let's look at y0 divided by EH. Okay. This is equal to Z0. Z0 here is y0 divided by EH. Okay. And then we subtract off AL. For some reason we want to do that. And then we square this. And if we do that, using the XY formula that we have up here, we see that we should take the first factor and magnitude square that. So here we get y0 divided by EH magnitude squared. Okay, minus 2 times the real part of y0 divided by EH times AL conjugate, and then plus the magnitude squared of capital AL. Okay. So just use this XY formula here on this. Okay. So why did I do this? Well, if we look here, we see that this part of the expression is equal to this part of that expression. Right? Minus 2, the real part, AL conjugate, y0 divided by EH plus AL magnitude squared is what we have here also. Okay. So we can replace the red part here with the left-hand side minus this. So if we continue the calculation of the distance dl squared, we can write this as EH ER divided by EH. And then we have the red expression, and the red expression is this minus that. Okay, so it will be plus y0 divided by EH minus AL magnitude squared, and then we need to subtract off y0 EH squared with this, and then it should be parentheses like that. So this was a long derivation of this, but now we're almost done. What can we deduce from this? So what we're trying to do is to look at the, okay, so this is equal to, that's what we started with. It's the distance to the nth simultaneity squared. Okay, so this is what we want to compute for different L's. And then we would like to find the smallest of these distances, and then we use that to base our decision in the minimum distance receiver. Okay. What we have shown now is that we have this is equal to that. Okay. Why is this good? Well, so basically we would like to compute this for different L's and find the one which is the smallest. You agree? For different L's, we would like to compute this for all L's and then find the L which corresponds to the smallest distance. So if we look at the left-hand side here, what of these things here depends on L? Okay. EH, does that depend on L? No, it's the energy of the pulse. Has nothing to do with L. ER divided by EH, does that depend on L? No, it does not. Okay. This term here, does that depend on L? No. So the only thing that depends on L here is that this part is the only thing that depends on L. Okay. So I don't need to compute these things, which doesn't depend on L, because they will not affect my decision. The only thing that will affect my decision is this term here. So let's compute this for the different L's, and then pick the L which minimizes this term, and then we have the minimum distance receiver. Did you follow this? Because that's the crucial conclusion now. I'll say it once more, right? We would like to compute the distance for different L's. Okay? So we want to compute this for L equals 1, 2, blah, 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 up to m. That's what we want to do. And then we would like to pick the L which has the minimum value. Okay. Now, in the left-hand side here, there are many things, but there are only a few things that depends on L. So when we compare the different distances with each other, we just compare the things which differs between them, right? And the only thing that differs when we plug in different L's is this middle term here. It doesn't matter what this term is, because it will be the same for all L's. Hence, it has no impact on my decision when it's time to find the L which minimizes the distance. So I might as well just compute this for all L's. Okay. So let's do that. Okay. And what we see here, that this is actually equal to Z0 minus AL squared. Okay. Because y divided by EH is Z0 that we have here. Okay. Fine. So the task now is basically to plug in different ALs here until this becomes as small as it can be. Or another way to say this, let's find the AL which is closest to Z0. Okay? And that will also give us the L which corresponds to the smallest distance between the receipt signal and the different signal alternatives. Okay, so if this is not super clear to you right now, I recommend that you go through this at home and try to convince yourself that this is actually the case. Now, for sure, we know, we show a noiseless case, this makes perfect sense. What we have shown now is that in the noisy case, this implements the minimum distance receiver, and that is what we're looking for. Okay, and so let's take 15 minutes and then continue the derivations here.